So I want to welcome you. My name is Greg Lowry, and I'm interim head of and Hammerschlag University Professor of Civil and Environmental Engineering. Welcome to our webinar series, Faculty Insights, a 20-minute briefing, and thank you all for being here today. This is a virtual series, and in this series, faculty from across the College of Engineering will share insights into their research, its impact, and provide perspectives for the future. Following the presentation, you'll all have an opportunity to direct questions and comments to the speaker. So today we're going to hear from Mario Berges, who is a professor of civil and environmental engineering, and his presentation will be called Digital Twins for Autonomous Operations of Built Environments. So we all spend most of our lives inside built environments, and they've been carefully designed and engineered. They rely on complex human-made systems to function, and those systems consume a lot of energy. These buildings also shape how we work and collaborate and learn, and how we create value together. So in that sense, they play a very powerful role in producing human, social, and physical capital. So a big question is, how do we make built environments more efficient, more adaptive, and more valuable to society? So today, Professor Berges will explore that question for you. He'll share highlights from his research on developing tightly coupled, continuously updated digital models that allow us to better predict outcomes and reason about alternatives in a principled and robust way. He'll draw on examples from commercial buildings and space habitats and other infrastructure systems, and he'll show us how these models can design and operate the built environments of the future more intelligently. Mario's work is making our built environment smarter, more efficient, and more resilient in the face of growing resource constraints and a changing world. His research uses advanced data analytics and sensor-driven models to extract actionable insights from infrastructure systems, especially buildings, and he has an emphasis on energy efficiency in those buildings. He's a faculty co-director of the Smart Infrastructure Institute and directs the Intelligent Infrastructure Research Lab at Carnegie Mellon. His work has earned numerous recognitions, including Professor of the Year from the ASCE Pittsburgh chapter and CMU's Dean's Early Career Fellowship. Professor Berges received his BS from the Instituto Tecnológico de Santo Domingo, and he is a double CMU alumnus. He's earned his MS and PhD from Carnegie Mellon. So before I turn the screen over to him, I'd like to remind our audience to please use the Q&A feature at the bottom of your screen. Submit any questions to Mario about his presentation. Make sure to include your name with your question, and you can do this at any time during the presentation, and then at the end we'll address those questions. I'll moderate that session, that Q&A session. So Mario, thanks for being here today, and I will turn it over to you.
Thank you, Greg. Welcome, everyone. Let me share my slides. Okay. All right. So I'm here to talk about digital twins and how they help to make our built environment more operationally efficient, and also some of the challenges that lie ahead to make this vision a reality. Before you get too dizzy with the background video that I have in here, which I'll explain in a bit, let me move on. This is by no means an effort of myself alone. I have a number of students, some of which are represented here because their work is going to be featured, some who are not in the slide because their work just inspired some of what's in here, as well as collaborators across campus and outside of campus. In particular, I'd like to thank Dr. Flanagan, collaborator of mine in this department as well, whose work also features here, because we co-advise some of these students who are on the slide deck. All right, at a very high level, I like to think about engineering as an optimization game. We're given a problem as engineers. We find the optimal use of all the scientific knowledge and existing knowledge that we have as humanity in order to solve it. And the problems that we solve are quite wide-ranging. It could be design problems to figure out what are the dimensions or the design features of some product. They could be operations, so sequences of operations, control objectives, controllers. All of these are engineering problems that we solve, and we solve them with existing knowledge. But I'd like to pay particular attention to the fact that we distill all this scientific knowledge into models of the world. And one of the main impediments to solving the problems that we have is that we have limited knowledge. And our models are wrong, all, but some of them are useful. And yet, the scientific enterprise that we humans have been embarking on since the Enlightenment has taken us pretty far. We've even ventured out into space. And so this is where I'd like to start the story. About 7 years ago, we were awarded a NASA project. That NASA project was particularly focused on figuring out how do we design technologies for deeper space exploration. We have been able to, using all of our scientific knowledge, get to have manned missions and space habitats that are situated in low Earth orbit, that are consistently being updated, maintained, and used. But NASA has a strong desire to advance deep space exploration, and so does most of humanity. And this will require that we figure out how to take all the knowledge that we've built to enable this further into space, where there's going to be a lot less support from the Earth resources that we have. So let me tell you a little bit about that. A whole lot of scientific knowledge that we've developed and the models that come down from them are what keep the operation of satellites and systems that we have on orbit. And that knowledge is very useful. In fact, so useful that we rely on it with fast communication in order to diagnose things that are going wrong, to figure out how would we play out some particular operation in a future scenario. We use even, for example, physical copies of the systems that we have in space to do what if scenario analysis here on Earth. And we can send the resulting optimization result into space and then get quick feedback. But that's all because we have very short distances. Once we move out into deeper space, there's going to be slower communication because of delays in communication. In addition to that, we're going to have less humans around. We're not going to have everybody joining those missions. So we're going to have very little support. And this pushes the boundaries of what we can do with existing models and existing scientific knowledge once we are in those situations. So that's the starting point of my talk. This is a motivation. These are the challenges that I'd like to frame my talk around. So as I mentioned, this was precipitated by a NASA project that I got about 7 years ago. And it was a highlight of my career. I got to work with astronauts, engineers of various disciplines, architects, psychologists. My main contribution in that project was to suggest that we leverage all of the existing digital representations that we have of our body of knowledge on Earth and bring it on board. This would be CAD drawings. This could be any other digitized information. So for example, we could take a space habitat and we already have CAD models of all of the physical assets that are in there when we design these systems. But even after sort of suggesting that, quickly I realized that it's not just about having the representation, it's about being able to use it. And so let's say that there's a problem, there's a CO2 leak somewhere in the space habitat. How do you know exactly which valve to close? This process of understanding all of this information and then making it useful is a very relevant one, especially when you have communication delays and you're out in space. So the motivating question for that process was, can we make quick decisions to optimize these systems without having to rely with the expertise on Earth, both the models and the people sort of sifting through them? So how do we make quick decisions without Earth assistance? And by integrating all the models together, this is what I will call a digital twin, is all of these models together. And developing custom software-based agents that could use them, we made significant strides towards that objective. I won't tell you all the details about it. I'll just tease you that we got AI to do what would take 47.5 years to only take 2 weeks of training in order to get there. And I will then detail what that means later. Before I do that, I'd like to just pause for a moment and make sure that when I mention digital twins, you all have the same idea that I have in my mind. Okay, so we'll start with like very basics. What is a digital twin according to me? So a digital twin is basically a coupled pair of a physical asset and its digital representation. And that coupling is done through sensing and actuation threads going to and from the physical and digital assets. And that keeps it, those threads keep the two in sync. And just as there are components in physical assets that are static and behaviors that these components have that are dynamic, we also mirror those same things in the digital realm, but we do it with information models that keep sort of the static geometry and all the other properties, and simulators that basically tell us the time evolving behavior of these systems. Um, Typically, though, even though we have access to all these models, simulators and information models and so on and so forth, when we are giving an engineering task, let's say, for example, let's control the altitude of some spacecraft that was going out, or to bring it back to Earth, let's make sure that energy consumption in the building is low. We don't necessarily take all of the models and then use them in synchrony to deliver our solution. What we usually do is we synthesize a particular portion of that set of knowledge that is in the digital realm, right? And so that little model, that baby model that is in there, then we embed into some control loop. And this control loop, again, I'm talking about a very wide version of the control loop. It could include a control loop that is based on optimizing the design over years of a particular asset. But that is what we do. We basically take all of the knowledge that we have, digitally represented, and then make a small version of that available for a very specific objective or optimization objective that we have in mind. So we leave behind a lot of the potential digital twin that could actually answer more questions and allow us to optimize for different objectives than what we currently have at any given point in time. This is also true for how we actually do this in space habitats today. We have the space shuttle out there, sorry, the International Space Station out there, and let's pick one particular controller that could be in there, the one that keeps the CO2 levels at bay. It doesn't need to have access to the full computational fluid dynamics of the air molecules moving around the space habitat, because that may be inefficient use of what it is doing. But instead, it has a very simple model that maybe measures some specific quantity and then has a threshold that activates a particular CO2 scrubber, for example. So that's kind of what we do right now. And if we are able to take all of our digitized assets into space, that would still not solve the problem, because in reality, it's even worse. Mission control, which is sort of the knowledge source for all of the operations, is actually composed of more than just digital models. It's also composed of humans that have a lot of non-digitized models in their head and information. So how do we, take all of this into space is a motivating question that this NASA project allowed me to do. And in particular, over the course of the last 7 years, what I've been trying to do to answer this question is to provide two particular research paths. One focused on how do we enable a universal software interface with which to exchange information between the physical world and the controls that we have and all this body of knowledge. So what does that software interface look like? And then the second one is like, because it's going to be a federation of models that we have in there, how do we orchestrate and integrate them all together? That's a sort of second high level question. Okay, so in light of that, and that's sort of the backdrop, I'm going to go over two case studies. And those two case studies will provide us with a flavor of how this is done in practice. And then I'll close up with some future directions and open up for questions. Okay. All right. So case study number one, optimal heating and cooling of buildings. We are spending more than 90% of our time in built environments, especially indoor environments. And these environments are the ones that are dictating how, as Greg pointed out, physical, social, and human capital is developed. How useful are digital twins in allowing us to optimize this exchange from raw capital to social, human, and physical capital? And what's missing? So I'll start with, again, with a motivating question. If I were to just take this particular example of optimizing energy use, given heating and ventilation and air conditioning, I might ask a smart AI, can you optimize my temperature while keeping my costs low? And if you ask that question today to the academic community, they will give you sort of two answers. There are those, mostly engineers, who think that we can model the building perfectly. And once we have these models, then we can predict how the models react to any given input and optimize those inputs so that we can achieve our objective. And then on the computer science world, or people who are not interested so much in models, they just say, hey, we have this reinforcement learning paradigm that allows agents to explore the environment, interact with it, and learn a policy that maps from the existing states of where you are to what action is optimal. The problem is that if you take the modeling route, every building is different, and you'll have to model each one of these buildings perfectly, or as well as you can. That takes a lot of engineering effort. And if you say, well, models aren't important, I'm just going to learn from data, well, you're going to spend a lot of time until you actually learn that policy that maps from the current state to what's optimal to do. And so what is a practical and scalable solution for building control? That's a question that we in my team asked ourselves a couple of years ago. And not to belabor the point, but all buildings are a different target. And so we will need, no matter if we do data-driven or if we do model-based approach, we will need to adjust either by paying in time or paying in engineering effort to model these things. So when we started working on this, there was a bunch of literature on doing this with the data-driven approach, the reinforcement learning approach. And what I'm plotting here is the papers that had come out there producing solutions. And I'm plotting them in time with the amount of training time that this reinforcement learning agent required in order to produce a good result. And notice that this is in log scale. So we're actually talking about years of training time, mostly in simulation, to get these agents to actually control the heating and ventilation properly. So all of them above 1 year. In particular, there is one example that we noticed, and we made an effort to try to use that as the prototypical example to see how much we could improve. And that example took 47.5 years of simulation time. So the agent was interacting with the environment for 47.5 years, not clock time, but simulation time. And then it was able to control the building correctly. That same building, once we allowed a digital twin representation of the building to be accessed by the agent and used in the optimization loop, we brought it down to just 2 weeks of training time. So what are the aces up our sleeve that we used? Two particular approaches were important. One was imitation learning, so allowing the agent to look at historical data of how the building is operating, and then use that to train its policy in a way that is more efficient. And then during the online behavior, so after I trained on historical data, I'm using physics knowledge, so particularly models that we have of how the thermodynamics should behave in a building in the context of a optimization routine, model predictive control, in order to be more efficient at how I use the data that I'm collecting online. This is probably going to be the only technical slide that I have, but I think it's useful to show how the actual models take place here. So on the offline side, we just take historical data from the building automation system and allow the agent to try to imitate what the existing controller is doing by using a policy that encodes the actual physical behavior of how we think thermodynamics behave in a building. and then tries to learn how to do that appropriately using historical data. Once historical data is done and we've sort of pre-trained our model, we go into the online learning. We let the system loose with the actual controller, and then it takes observations from the real building and then adjusts again its policy based on that. But it is much more efficient because it has models. It has the knowledge that we have obtained over, our scientific enterprise over decades in order to be more efficient about how it integrates the data that it is collecting. So we put this in a number of experiments. I'm just going to talk about the latest one, which happened earlier last year. So we partner up with people at Purdue. They have an electric house on campus that has a heat pump and all electric appliances. And in that particular house, we had indoor air temperature as our state. We wanted to figure out what was the indoor air temperature, and we were only able to control the set point of the thermostat. And obviously we had some disturbances, we couldn't control the sun, we couldn't control the outdoor air temperature, and those things we modeled, their effect on the temperature we modeled. And our objective was to minimize the total and peak energy consumption and the temperature deviation. How far is it from the set point? We played this on a 24-hour horizon of control, and we applied control inputs every 60 minutes, trained for 30 days, validated for 15, and then did an evaluation at the end for 30 more days. I'll just show you the results because that's the interesting bit. So on the left, I have panels that show a prototypical 24-hour trajectory of the building, where I'm showing the assigned set point, the user-defined set point, what the users wanted in green, and the return air temperature, which was our measurement of the indoor air temperature. And then on the bottom, I'm showing the power that, or the control input for the heat pump. Particularly here, it is important to say that in this heat pump, there was an electric resistance heat that was available to the heat pump if the building was not being heated up properly and you needed to heat it up faster. So we wanted to avoid that. And so that happens exactly after 4.2 kilowatts. And so in our optimization, we included that constraint. And we asked we didn't ask, but the optimization forced the agent to learn how to control the heat pump without exceeding the 4.2 kilowatt max. And so what it did in order to get there is that it basically started very slowly ramping up the power for the heat pump so that it could preheat and then get to the temperature that the users asked for on time. And then once it wasn't needed, it could actually go back down. And it learned all of this on its own. The preheating strategy was not something we set. It was just something that came out of the optimization process quite quickly. Actually, in about 2 days, it was already learning how to control the building. And then on the right-hand side, I have a panel that shows sort of the trade-off between the energy use and the outdoor air temperature. The moral of the story here is that compared to a engineered solution with model predictive control, our solution, this RL solution, is actually quite indistinguishable. We still got a 22% improvement in energy savings compared to MPC. That got 20%, but that 2% difference is not what's important. What's important is that this only took 2 days without any engineering effort compared to months of engineering time to create the models. Okay, so I'm going to do one more case study and then open up for discussion. Second case study that I want to talk about is now, okay, so we have models of the physical system. What about the humans who are in it? Shouldn't we model those too? And how do digital twins extend to that? So I'm going to talk about predicting occupants' behavior and their preferences. In particular, to motivate that, I want to put 2 facts that we found recently. One is that when you have these controllers like the one that I showed you before, and you test them on non-deterministic occupancy, they break down. If you don't assume that you know what the occupancy schedule will be, it becomes harder to optimize things. So knowing where occupants are and where they will be and what they will need is important. The second one is that occupants also affect the parameters of the model. say you go into a house and you open windows. Well, window opening changes the thermal resistance of that wall enclosure, and that creates a change in your model parameters. In fact, this change, just to illustrate the point, is very evident in existing data sets. This is a busy slide, but what I'm trying to say here, just focus on the range or the spread of two slides of the two decks. On the left, we have 1,000 homes over the United States that have a smart thermostat. And what I'm plotting here is the time constant for that home, the thermal time constant, how quickly it reacts to changes in temperature. And then on the y-axis, I just have all the houses, all the 1,000 houses ranked. And as you can see, it's shorter spread of RC values of the time constant, centered at around 5. Whereas in the heating season, it's very different, and the spread is much larger. And this is because during the heating season, we suspect there are people who open and close windows, which changes the RC time constant significantly. So what I'd like to propose is that because human behavior is so important, we need to sort of extend our digital twin framework to include human users. Again, the physical and the digital side. So how do we do that? We actually need two things, and that's where I'll close the discussion. One is we need better sensing. We need to better inform our models by actually capturing behavior of humans. And in the past, and this is how I'll relate to the first slide, I have been investigating these types of sensors. So we've deployed cameras that measure distance from the camera to everything that's under it, and then use that to estimate how many people are coming in and out of a space, for example. And using that information, you also capture things that are not as useful. So for example, in this particular camera that we were using, which was using infrared, the distance from the camera had to do with the how much the material absorbs the infrared. And curly hair absorbs infrared differently than non-curly hair. And so we had to adjust, and this is sort of an aside that is important to note, that as we collect more data, we actually may be collecting data that is not useful or not very well calibrated, and we need to take that into account as well. So data is the first one, collecting more measurements to understand humans. But the second one is we'll need models, and we'll need models that can allow us to say, hey, if I give you these 6 configurations and I model how these configurations look in space, I also model how in this particular configuration, light intensity is distributed, temperature is distributed, and shadow is distributed. Could I use those models to predict how people will move around in these spaces? That's an important challenge, and it's one that we and my team are working on to create agent-based models that are informed by data in order to understand social patterns and social dynamics. So at the end, we'll need many, many explicit models, actually. And the question is, how do we make them all work together? And I'll stop in this particular slide because this is where research starts, and it's probably a good segue into discussion. So with that, thanks, and I'm happy to take questions from the audience.
Great. Thanks, Mario. Digital twins are amazing, and the insights you provided here have been extremely useful. We do have a number of questions rolling in. I will remind folks to add your name to the question. It helps us keep track. As questions roll in, there are a handful in there, but as they continue to roll in, I want to ask you a question. And I know we've talked about this a little bit, but you're tracking people in these buildings, right? You got cameras on people, and not everyone likes to be tracked all the time where they are. So what are the privacy issues or concerns about this approach, and how do you manage that?
It's a great question. I think I don't think of myself as a privacy researcher. I think of myself as an engineer that should consider privacy in designing these solutions. So from my perspective, what we try to do is we try to, from the design of the solution, think about the privacy of the individuals from the get-go. So in particular, for example, when we were deploying cameras, we didn't use full red group RGB cameras that collect color. Instead, we deployed depth sensing cameras that just collect the distance of every pixel to the camera. So that's a lot less privacy invasive because you only have distance. And also we're mounting the cameras looking from the top down so that you would only see blobs of head coming in and out. Still, there are privacy implications of this, of course. Um, but I think that at the end of the day, I'm trying to provide solutions that their adoption in society will require a wider discussion because it's a wide-ranging set of questions that we are not ready to answer at the moment, and it would require input from a lot of different folks. But it's a great question.
Great, thanks, Mario. So, boy, there's a bunch of questions. We'll try to get through as many as we
Sure.
possibly can. So let's start with a very general one. Justina asks, sort of, what are you most excited about in regard to this research in the next few years?
Ooh. Um, so at a high level, what has me most excited is that we are now in an age where machines can read, understand, see, and even reason to some extent. And so many of these things that I was alluding to at the beginning that required human expertise are slowly being replaced by, for lack of a better word, agentic AI that allows us to put it in place and complete the control loop without a human in there. Doing that effectively, again, with all the privacy implications and with all the societal values upheld, is a very interesting research path. But it's one that I see as very promising, and the acceleration of these technologies is just faster and faster as we go. So I'm very excitedly tracking that set of developments.
Great. So another question here. This is a bit more technical, but it's a pretty interesting question. So, um, the question comes from Christian. How do you ensure that you'll have a complete data set to answer the questions that you're trying to answer, right? How do you handle missing data in that process?
Um, Again, that's a great question. I think it's a question that science has been grappling with since the beginning of time, right? I think we cannot collect all the data about the world. We can only have um, the data that we can, and then we create theories or hypotheses of how our models fit the data or what is the right model to fit the data, and then we test that. And over time, we develop more confidence on the models that we have and then extend the reach of those models. Um, that's a very philosophical answer, but that's kind of the same philosophy around doing this with any model. We will use the data we have, cautiously create a hypothesis that would allow us to fit the model to the data. And then we can't extrapolate from there because we don't have data out there, but we assume that it works and then we test. The other side of that coin is that we can use the model itself to inform us about the uncertainty that we have in different regions of the model's input. And so even though we don't know if it works or not, we may be able to say, hey, we are very confident about this because we have a lot of data in this region. We're less confident about this other side. And so maybe that is where we should be collecting more data as we go forward.
Great.
Yeah.
So, question came in about students. So
Oh,
how do you involve your students in all of this research?
it's a great question. So, all of my research is carried out with PhD students at the very minimum. My lab also involves master students and undergraduates, each in their particular role. But for all the research that I presented here, there is at least one PhD student whose main goal is to take this project to fruition. And then they surround themselves with either other PhD students, master students, or undergrads as needed in their journey. In fact, if I may add there, like many of the test beds that we have, like the actual buildings that we're testing, are student test beds, like student homes, for example.
Nice. Yeah, I see the students running around with the sensors a lot.
Yeah.
So here's a question from Raul, which is an interesting question about AI-based solutions in general. So, what do you think about validation and liability issues with these AI-based solutions?
Um, okay, so I guess I'll piggyback on the answer that I gave earlier. Like let's start. Like all models are wrong and some are useful. So the plan for validation has to do entirely with what we think our model is capable of. And so we should be validating our models continuously as we gather more data, as we subject these things into new domains where we hadn't collected data before. The liability issue is more of a societal problem than it is an engineering problem. Like these models are not going to be perfect because no model will be perfect. If you had a model that was perfect, you basically recreated the world. And so we will have always this dilemma of figuring out, like, under this uncertainty of predictions that these models make, how do we balance the risk? And that, again, is, in my mind, not just an engineering problem. Different settings will have different tolerance for different risk profiles. And so it's a ongoing discussion with the decision makers and the people at the other end of those decisions.
Cool. Thanks, Mario. So, a few people are sort of asking about other kinds of applications. I know you gave a few examples, but what are some other kinds of applications and sort of maybe applications in the civil engineering domain space? I don't want to read too much in the question, but maybe that means like building bridges or roads and these kinds of things. So what would you say to that?
Yeah, so I think at a high level, digital twins as the keyword that we're using here is not that different from digital models that we had before. The main difference is that we're now tightly coupling them with a physical asset and trying to keep them in sync. And that we are supposedly making models that can extrapolate and can perform counterfactual analysis, which may not have been true for the other models that we had before. But engineering, the engineering discipline has been doing this forever. So you mentioned transportation, you mentioned structures. All of these rely on models to make predictions about how things behave, and then using those predictions inform the decision. So in all of those cases, digital twins are also becoming important. But because of the tight coupling, it's mostly in the places where we have a lot of sensors and a lot of actuators that they are cropping up more readily. I'll give you a couple of more examples, just that didn't have time to mention. We have been making digital twins of railway assets to inform the monitoring and preventative maintenance activities on rail. By collecting data on board the train, we inform our models of how the rail is behaving, and then sort of direct operations according to what our models say. So that's one example. I've also been using models of the local weather to figure out, for example, where do I place cooling stations for a heat wave in a city? Again, these are models, but they are tightly coupled because we do have sensors across the city that collect temperature measurements, and then we use those to update what our model is saying and then make derive decisions out of it. Um, so it's a very broad set of applications. I'm only scratching the surface here.
Yeah, the digital twin world and predictive modeling is an exciting space for
It
sure.
is.
Lots of room to grow here. So here's another question that came in from Rahim, and it has to do with the applications of these models, and he's asking, have you investigated the cost benefit of implementing digital twins? Um, you know, Data collection and analysis and the savings from optimizing energy performance, sort of putting all that together in a cost benefit analysis.
So not directly is the quick answer. So I haven't performed an actual cost benefit analysis with all the numbers. But our hypothesis is, as you saw in the use case, case study number one, that the cost that we pay to generate these right now with engineers to develop the models is not effective. Like the cost benefit ratio isn't good. So we should be trying to create these models more automatically. And so my example of how we do this with the agent that I showed in the presentation is one such way, where we take data, we just inform the agent about the general physical laws that it needs to obey, and then as it interacts with an environment, it is generating the digital twin of the space that it's interacting with. And I think that that's going to be sort of like the way forward, which is also why I'm very excited about using LLMs and agentic systems to facilitate the process of developing these models and make the costs go down.
Great. Makes a lot of sense. So,
Yeah.
James asks, can you share a bit more about the need for connecting or coordinating different models? Right? So, fit for purpose models for different applications, what makes it necessary for them to work together?
It's a great question. And it reminds me of a discussion that I've been having with other folks here in the computer science department and in other, even in engineering and public policy, because I think we're at the time now where the ability to model is becoming like our ability to model is becoming a lot more cheaper to implement, as I said before, that we can answer questions that we ordinarily would have taken a lot of time to answer. And I'll connect that back to like why different models are needed together. So say for example that I'm interested in knowing uh, the same question that I had before about figuring out where to place the cooling stations for a heat wave in anywhere in the US. Um, if I were to do that for today, I don't need any climate model. But if I were to say in the year 2050, where would that be? I need to couple my model of where the cooling stations should be with a climate model. And if I also need to say, well, what about then the costs of doing this and what will people be doing in 2050? Then I need an economic model to tie to that and so on and so forth. Like the models are there. I think the question right now is figuring out how to integrate them all in order to answer more complex questions than what we had been able to answer before in isolation. Um, that's a very generic answer, but to me, it's the way forward. Like if we have the models, integrate them together will directly enable us to answer more complex questions than what we currently have.
I suppose technically, if you integrate enough of them, we can have a model of the world.
Exactly. That's where this is heading towards.
That's that. Yeah, I think we're a bit a ways from that, but
Yeah, very far. But
so, okay, so here's another question. So Christian's asking about sort of how do you connect the humans into your system? I know you got some sensors and you look at some mobility, but what are the challenges to integrating the human behaviors into all of these models?
yeah, so I sort of sped through those slides near the end that had to do with that. I think there's a whole bunch of challenges in here. I mentioned that the big two are getting the data about where humans are right now and what they're doing and how they're behaving so that we can then, challenge two, create the models of them. But then even if you do those two, I mean, there's additional challenges. Like how do you then derive the right actions that would trigger changes in human behavior? So we may have models, but like, how do you nudge people to do the right thing? How do you ensure that your physical space and its interaction with the humans around it are behaving how you want? Um, and then there are the transversal themes about privacy, security, autonomy of the people in it. Because you don't, the autonomy piece is slightly, it's even more insidious because once you close the loop around the human, then you have to ask yourself, like, is the human making the decision autonomously, or is it the whole system that is autonomous, right? There's many levels of questions to do here. I don't know if the question had a particular flavor that I didn't answer there, but that's a generic, high level answer.
Yeah, I think the challenges of predicting human behaviors in any setting is definitely a challenge.
Indeed.
Okay, so Mike is asking you a question, and I'll broaden it a little bit, but very specific question. Are you seeking test buildings internationally? I guess I'll expand that just a little bit to say sort of what are your plans for test beds and for going out into the real world and testing these things out?
It's a great question. So currently, most of our test beds are local for various reasons. First, we have a very nice interaction with the facility management office here on campus. It makes it easier from a programmatic and logistics standpoint as well. But we are actually interested in expanding. It's costly to deploy these systems, especially those that have to also take into account humans and their behavior. But just answering directly to the international aspect of it, the how did I say this? The how easy it is for people to accept this varies widely international, like over the world. So it may be possible for us to collect more data and get more information from humans in other locales than just here. So we are always looking out for opportunities. And so if you know of any, I'm all ears.
All right, there's still more questions rolling in. Um, so, some of what you do a lot with buildings and building energy and predicting things. And a question here from Raul is about how can you bring in weather and weather predictions into your models in a way that would help you manage building energy use better?
Yeah, so I think the easy answer is that we need it for everything. Like weather is one of the main factors influencing energy use in buildings. So right now, what we do is we just rely on the existing weather prediction models out there. We use forecast of weather, local weather, on the 10-day ahead horizon, for example, and then just incorporate those into our predictions. I think where it becomes more interesting, because that's the generic answer, everybody will say the same thing. Where it becomes more interesting is when we think about local weather patterns at a more, when I say local, at a more spatially resolved and temporally resolved resolution, right? So if I had, multiple buildings next to each other and I wanted to know how the heat exchange between the buildings and the urban canopy affects the energy use, then that requires a lot more sensing. It requires that you model the actual canopy, and then you make predictions based on that. And I have a couple of efforts in that direction. It's not clear yet that the cost benefit ratio on that is positive. But it's an extension of the existing way that we use weather forecasts, which are more global and sort of less resolved.
Great. Well, thanks. I think we're getting close to the end of time here. So let
Sure.
me thank you, Mario, for,
Oh
for
no, my pleasure.
the amazing work that you're doing in this digital twin space. Very informative presentation. I certainly want to thank all of our audience members for being on the line today and learning a little bit about digital twins and the great questions that came in and the interactions there. I'll make a real brief announcement. Our department does offer a certificate in digital twins, where you can look at what is a digital twin, how to develop a digital twin, and then applications of digital twins. And so, have a look at that certificate program if you're interested in this topic. And it's not just civil engineering. It's
Yeah.
it's it's really basic fundamentals that can be applied to all kinds of different systems. Last thing is please keep an eye out for a follow-up email. It'll soon come out, and there's a link to this session that's been recorded. So I want to thank everyone for being on the line. Appreciate your time, and take care.